Thank you for being here with us, taking time out of your busy schedules to be with us today. I'm sure you've heard a lot about a lot of the performance and power optimizations and the performance per watt advantages in Agilex. So today I'm going to try to give you an inside-the-box view of how we achieve these performance and power improvements in Agilex. And I will also briefly discuss some of the advanced capabilities in our timing, power, and thermal analysis tools. So without further delay, let's just dive in. Agilex is Altera's first FPGA that is fully designed and manufactured within Intel. At the core of Agilex, we have our next generation core fabric architecture that is developed on top of a customized version of Intel 10 and Intel 7 process nodes. This combination of advanced core fabric architecture combined with enhanced process technology delivers 50% higher performance or up to 40% lower power compared to our previous generation devices. Agilex also comes with a variety of network and memory interfaces. It comes with multiple options for transceiver chiplets with lane speeds up to 116 gigabits per second. We also feature coherent processor attach with CXL in Agilex. And in terms of memory interfaces, our mid-range devices support DDR4 and LPDDR4, whereas our high-end devices support DDR5 and HBM2E. Agilex has also been extensively co-designed with our Quartus Prime Pro design suite and with many, many leading innovations that I will talk about later in this presentation. And if you look at all the different architectures, Agilex represents the spatial architecture with unique advantages in reconfigurability when you compare it to other architectures like a scalar CPU or vector GPUs or matrix AI processors. In terms of packaging, Agilex uses Intel's embedded bridge interface technology that helps us separate out the transceiver silicon from the main FPGA die. We use EMIB at 55 microbump pitch densities for interconnecting different dies onto a single package at a lower cost compared to using silicon interposers. In addition, by disaggregating, by using EMIB, we are able to use the same transceiver across multiple FPGA families. At the same time, we can also pair different transceiver chiplets with our main die, depending on what the customer needs are. Disaggregating the transceiver also gives us the ability to scale up the logic density of the core fabric to very large capacities while keeping the fabric monolithic. And that enables ease of use quite a bit because we don't have to partition workload applications into multiple dies, and it completely avoids any kind of loss in quality of results that comes as a result of such partitioning. Now let's take a look at the core fabric architecture of Agilex. So similar to Stratix 10, each fabric sector has many columns, particularly columns of programmable logic with distributed memory shown in blue here. You have 20 kilobytes of memory banks that are shown in green, and you have the DSP columns shown in purple. In Agilex, we significantly improved the performance of the core logic blocks, the programmable logic blocks, by 50%. And we also improved the capabilities of our DSPs to support emerging AI workloads. In particular, we doubled the per DSP throughput for various precisions like bfloat 16, FP19, FP16, and int8. Agilex uses an H3 clocking configuration that we had first introduced in Stratix 10, and it also does clock routing within our Quartus design suite. In addition, what we did was we introduced programmable delays on the clock network that Quartus can intelligently use to improve the performance further. Programmable hyperflex routing ties all these blocks together. And routing is the single biggest contributor for performance, power, and area on an FPGA fabric. And it went through the largest transformation in Agilex. So let's just briefly talk about what are some of these routing architecture improvements that we did. So if you look at a typical routing segment that crosses 4 columns in Stratix 10 and prior architectures, it starts with a wide mux, followed by a buffer that feeds a wire that crosses these 4 columns. And along the way, this wire also fans out to other muxes across the architectural column boundaries. Now, this high fan-in, high fan-out routing architecture worked really well for many generations of Stratix family of FPGAs. However, it did not scale very well for Intel 10 and Intel 7 process nodes. So we completely redesigned the routing architecture to use narrow, faster muxes and that fan out to a single destination row or column. We also redesigned the routing patterns. We adjusted the routing muxes on the routing network for improved routability compared to our previous generation. Now, if you look at the chart at the bottom, this shows sort of the routing delay that spans across these 4 columns, with Stratix 10 shown in orange and Agilex shown in blue. As you can see, we achieved a significant improvement in the actual delay of these routing segments in Agilex. Now, global routing does not directly talk to the logic blocks, the programmable logic blocks directly. There is a sparse crossbar of signals that funnels thousands of these global routing signals to a few logic input pins. And in Stratix 10 and prior architectures, the internal structure of this crossbar had many long lanes with wide muxes and lots of fan out. So in Agilex, we completely repartitioned this and redesigned this crossbar, where we now use narrow, faster muxes, faster lanes that have a reduced logic span while retaining some of the long lanes with reduced fan out. And this resulted in significant improvement in performance, as shown in the chart on the bottom right there. So here you see the delay across every path going through the crossbar, and you see Stratix 10 shown in orange and Agilex in blue, and it was significantly faster, on the average about 2.5x faster, the actual delay. Okay, so this was a big contributor to the performance improvement in Agilex. The other part is we co-designed our placement algorithms in Quartus with this architecture to align placement logic very close to these fast crossbar lanes. Okay, so Agilex features a next generation version of our HyperFlex architecture, which was first introduced in Stratix 10. And in this architecture, we feature programmable registers everywhere in the fabric, on every interconnect segment, on the inputs of logic blocks, etc. And in addition, Agilex also features this ASIC style clocking architecture, where we actually do clock routing based on the locations of the flip-flops that the placer determines. But more importantly, we enhance the clocking network with these programmable delays that Quartus uses to improve the performance. And I'll talk a little bit more about this later in another slide. Our Quartus Prime Pro software was really co-designed with this new HyperFlex architecture, building in fine-grained retiming and retiming awareness in the entire flow. In addition, we have late-stage global retiming steps as well as clock skew optimization steps that work with very accurate sign-off quality multi-corner timing analysis. And I'll talk about this in a bit. So let's understand the FPGA design implementation flow. So if you look at the traditional FPGA design implementation flow in Quartus or other tools, you start with logic synthesis, where you're taking your RTL description, elaborating them, and creating logic gates and doing technology mapping. And then you follow it by periphery placement and clock allocation. And once you've done with that, you take all the logic elements and cluster them into the underlying primitives of the FPGA, like ALMs and labs, and then you place all these elements on the actual FPGA fabric. And then finally, you route all the user design the connections using the underlying programmable routing fabric. Physical synthesis is a step that is mostly done in the pre-route stages of this flow, where you're surgically fixing critical paths as they appear in the flow, and it's powered by incremental timing analysis. With our new HyperFlex architecture, we revamped the entire Quartus implementation flow to be very retiming centric. We introduced late-stage global retiming steps and clock skew optimization steps where we can improve performance optimally with sign-off quality timing analysis. But more importantly, we can do that without the need to reroute any connections because the fabric has built it in. Second is that we also introduced a post-route physical synthesis step that does many different optimizations very late in the flow with very high quality timing analysis. And this is done surgically to fix certain critical paths to extract a lot more performance. Now, that's all not enough to just do retiming and clock skew. What happens to the earlier parts of the flow? The synthesis, placement, routing, the core engines themselves have been revamped in the last several years significantly to be state-of-the-art engines. But in addition, we took it one step further and made these engines retiming aware. What does that mean? It means that these engines can now fix critical paths that cannot be fixed by retiming later on. So they're operating and trying to optimize the right critical path. So you kind of get the best of both. So with all these improvements, we have achieved over 1 speed grade advantage of Fmax improvements compared to our previous generation. Now let's understand logic retiming. Logic retiming is a sequential circuit optimization technique to improve performance by minimizing the number of registers used for that optimization. Retiming modifies the circuit structurally by moving registers forward and backward across combinational elements as well as across interconnect elements. So as shown in the pictures below here. In Quartus, we have a global mathematical formulation to solve the retiming problem optimally, where we consider all the retiming constraints and the timing constraints and come up with the optimal performance. In addition to global retiming, we also have stages of incremental retiming where we can surgically fix paths along the flow as critical paths appear. Now let's understand a very, very important topic, which is on sequential equivalence. So let's take a simple circuit here that has 3 gates and 3 flip-flops as shown. These are simple D flip-flops, same clock, nothing fancy on this design, right? And let's say all we're trying to do is forward retime that flip-flop F1 forward onto the fan-out branches to give you a circuit like this. So now that flip-flop F1 has become 2 flip-flops, F1A and F1B. How many of you think that these 2 circuits are completely equivalent? It's a pretty benign move that we've just done, right? Okay. So as it turns out, these 2 circuits are not equal. Okay? Let's understand why that is. In the original circuit, if you apply the vector A equal to 0, B equal to 1, and clock the circuit just one time after you power it up, regardless of the initial state you powered up, it guarantees that all the 3 flip-flops will enter state 0, and your output of that circuit H will have value 0. Okay? The logic has been constructed as such. Now, in the new circuit, in the retime circuit, if the retime circuit powered up on F1A equal to 0, F1B equal to 1, F2 equal to 1, and you apply that same vector in one clock cycle, it turns out that you get H equal to 1. So the retimed circuit exhibited a behavior that the old circuit cannot exhibit. So by definition of sequential equivalence, these two circuits are not equal. That was a pretty benign, simple move, and these two circuits are not equal. How do you deal with this, right? So we crafted two very interesting solutions for this. So the first solution introduced programmable initial states in the hardware, meaning all registers upon configuration power up on a known initial state. Let's say value 0, for example. So when we retime the registers, we ensure that we maintain those initial states. So for example, in that simple example of a NAND gate where we retime the register backward, you compute the initial state of the registers on the input as value 1. So later when we configure the device, we can ensure that that state is maintained. This technique works well, but it is limiting because there are some cases where the retimer will get stuck and you cannot compute an initial state, as shown in that fan-out branch example, where you have two flip-flops trying to retime itself backward, one with state 0 and one with state 1, and you cannot retime at that point. And this limits the amount of Fmax you can get because the retimer is limited. The second solution is what we call C-cycle retiming, and this is one of our innovations where we show mathematically that a retime circuit is a C-cycle delayed replacement of the original. What does that mean? It means that you can compute the reset sequence of the retime circuit by prepending C empty clock cycles to the original circuit's reset sequence. So if you look at the two circuits I showed earlier, it turns out that these two circuits are equal with C equal to 1, which means you take the retime circuit, you power it up, you clock it once with random inputs, then you apply that original reset sequence, and the two circuits are indistinguishable. Okay? Now, where does the C come from? The retimer computes the value of C pessimistically. And this gives us a lot more flexibility during retiming because we can get further Fmax by doing so. Now, in practice, there are many registers that you care about and some registers you don't care about in your design. So the registers that you care about are marked as such in your RTL, where you specify the initial state. But the other registers that are not specified or generally don't care. So we have this hybrid mode where the registers that you care about, we maintain the initial states, and for the others, we do C-cycle retiming. So we can kind of get the best of both. Okay? And that's a default mode in Quartus. So if you care about a register's initial state, you probably want to mention that in your RTL. With all these retiming related optimizations, in our internal benchmark suites, which has pipeline designs, we achieve 25% average Fmax with very, very high confidence. Our physical synthesis optimizations also produce 13% average Fmax on our internal suites. It applies various techniques for optimizing the design at various parts of the flow. And here's the other beautiful thing, is that it achieves this with very little runtime overhead, on the order of about 7 to 8% on the average on our internal benchmark suites. So let's talk about clock skew optimization, time borrowing, and retiming. What's the relationship? So the circuit on the top, I mean, those numbers are showing the delays of those combinational elements and the interconnect. And you have two flip-flops, flip-flop I, flip-flop J. The target clock period is 3 nanoseconds, and the middle path there misses timing because its delay is 4 nanoseconds. So you could skew flip-flop J by 0.8 nanoseconds because the path on the other side, on the right, has positive slack, and you can borrow some time from there. If you skew that flip-flop J by 0.8 nanoseconds, then you can achieve a clock period of 3.2 nanoseconds. Now with retiming, you can retime very fine-grained on the interconnect and across the combinational elements, as shown in the two pictures below, where flip-flop I, you can move it forward, flip-flop J, you can move it backward, and by doing so, you can achieve a clock period of 3 nanoseconds. So this example kind of shows that retiming does better than clock skew. However, in general, the relationship is shown between clock skew, time borrowing, and retiming is shown in this Venn diagram here. And each of these engines have their own unique strengths. In Agilex, we introduced programmable clock delays on the clocking network that Quartus intelligently uses in late stage to fix critical paths and gain more Fmax. And on our benchmark suites, we achieve an average of about 5% Fmax just by clock skew optimization. This is on top of all the other retiming optimizations that we do. Okay? Okay, now let's just quickly switch gears on power optimizations. So if you look at the standard Intel 7 process, it delivered significant performance and power compared to the prior generation Intel 14 process. However, we got a lot more from Intel 7 by doing specific customizations specific for the FPGA needs. So in particular, we tuned the metal stack where we adjusted the metal layers, we adjusted the track width, the spacing, the aspect ratio, etc. for the metal stack. That improved performance. We also use wider polypitch for all the transistors on the core fabric for improved performance. And we tuned the threshold voltages for better power. Now, in addition to all the fabric enhancements, we also did a bunch of optimizations post-silicon and in our packaging technology. So for example, we use better materials for packaging that have much better thermal characteristics that reduce power. We use things like smart bin-based voltage settings for the different dies. We also do smart die pairing when we put dies together. And lastly, we improved all the margins that we have and reduced the pessimism. We also reduced the nominal voltage by about 100 millivolts. That led to further power reductions. Now, with all these power reductions, we relied completely on the core fabric hardware and software innovations to gain us the performance while operating at a lower voltage for purposes of power. So in theory, we could raise the voltage and get you even more performance, but we made that trade-off because we had made significant advances in the core fabric for performance. And with all these techniques combined, we get over 2x performance per watt advantage that you've heard about in Agilex compared to our prior generation Stratix 10. Okay, so now I'm going to move on to our analysis tools. So static timing analysis is an industry standard tool where you are trying to sign off your timing. All EDA tools provide this capability. And the essential job of a static timing analyzer is to compute slacks where you have setup slack and hold slack. So the setup slack is essentially the difference between your fastest required time and your slowest arrival time. And similarly, the hold slack is the difference between your fastest arrival time and your slowest required time. Now, timing analysis compute the slack on every node for min and max delays, and all the optimizers use this for purposes of optimizing the design for timing constraints. Now, it's also important that timing analysis has this full capability of multi-corner timing analysis that helps you sign off. In addition, there are many forms of incremental timing that all these optimizations use along the flow. Now let's talk about some of the advanced capabilities we have in timing analysis. So, advanced technology nodes have always subject to delay variations, especially on the clocking network. So to help with this, in Quartus STA, we compute something called a min pulse width slack, which basically tells you if you have any kind of clock duty cycle distortion that can make your design not work on board. So using the slack gives you an indication if you are exposed to this type of variation in your design. And what are things you can do is reduce the delay on the clocking network. You could reduce the chain of generated clocks that you use, or you can reduce the amount of clock gating that you use. So these are some of the things you can do to improve this slack issue. Another feature that all static timing analyzers have is about combinational loops, where the analyzer has to break the loop, otherwise it'll go in an infinite loop. The industry standard EDA tools, they tend to break this loop ad hoc in some heuristic way, and it may not correlate well with how the loop actually breaks in actual operation, which is data dependent. So it's not really 100% sign-off safe the way it's done. So Quartus takes a more accurate approach where we completely bypass the loop and we compute the min delay accurately using Dijkstra's shortest path algorithm. And for the max delay, we compute a pessimistic value by bounding the Hamiltonian cycle problem. So this ensures sign-off safety when you sign off on Quartus STA. So debugging everything that can go wrong on an FPGA is pretty daunting, okay? So Quartus Design Assistant helps you detect issues, and you can deep dive into solutions on candidate solutions once Quartus has detected the issues, as opposed to worrying about everything up front. If you look at Quartus, we have this feature for doing, for example, the asynchronous clock domain crossing checks that Quartus STA does. And Design Assistant is what reports any kind of errors you might see in that, in the handshake of the transfer, the multi-bit transfers that occurs across these clock crossings. You could use a constraint like a set max skew to the min clock period to ensure that all the bits are arriving consistently for these transfers. Another interesting thing is that if you want to see your timing critical path overlaid with other interesting metrics like congestion map to debug physical effects, this is a capability we have. So by doing so, you can understand what's physically going on with your design. So for example, in this design on the lower left corner, there is very high congestion near the HSSI IP, and your critical path sits in that area. So you could use this as a prompt where the insight is that you can maybe use something called a exclusive routing logic lock for all the soft logic connected to that IP, and that'll help you close timing. So this kind of views sort of gives you that type of insights that normally is not available. So let's move on to our thermal and power calculators. So we have two tools. One is called Power and Thermal Calculator, or PTC, and the second tool is Quartus Power Analyzer. So PTC is largely intended for early board designers, whereas QPA is intended to analyze the power and thermals of your Quartus placed and routed netlist. So if you look at PTC, the primary use case is for selecting and sizing the voltage regulators in early board design process. So board designers on high-end FPGAs, I mean, they have to power a dozen or more of independent power rails feeding the FPGA. And these high-end FPGAs also have sophisticated cooling requirements. So in PTC, we do thermal analysis for your design specific for your board, and we can tell you exactly what is the minimum heat sink capacity that is required to meet to keep the FPGA within spec. Now, board designers also typically lock down their peripheral pinouts as well as their protocol selections very early in the board design process. And by doing so, I mean, we have this tool called IP Wizard inside PTC that will help you instantiate some of these IPs. So you can quickly sort of evaluate the power and thermal impacts of those. So Quartus Power Analyzer, is used for generating or for doing thermal analysis on your design. So high-end FPGAs on complex applications can generate a temperature gradient, on the order of 10 to 15 degrees centigrade across the die. So Quartus Power Analyzer has this accurate thermal solver that will help you generate this fine-grained heat map of temperatures across the entire die. In addition, it can also show you the temperature at each of the on-chip temperature sensors that you can then use to cross-reference or correlate with your actual system measured results. So that's a pretty interesting feature. And just to give you more insights, the fine-grained heat map that you see is very well correlated with silicon by our manufacturing teams, where we have correlated the models with using infrared emission microscopes on the actual silicon. So this picture, the couple of pictures you show, like the top one shows there's a hot spot on the top right corner that silicon also shows, okay? So we ensured accuracy of these models to the best possible extent, and we'll continue to tune the models as we go along. Okay, so I'd like to conclude by saying, please try out our latest 24.3 Quartus Prime Pro software. It has many, many capabilities that we discussed today. The high effort flow of Quartus compiler has all the features that we talked about in terms of advancing the Fmax capabilities that we have. We also have all these advanced timing, power, and thermal analysis tools in this release. And it also supports Agilex 5 D-series FPGAs. And lastly, this has been discussed before, please share your workloads with us. This helps us evolve our benchmark suites to be completely current with the current problems that our customers face, as well as help us tune Quartus so that you can see better results in your designs. So with that, I would like to now invite, it is my great pleasure to invite Tim Mao, who's the CEO of Blue Waves Mobility Innovation, to share with us some of his insights of how they have partnered with us and used Agilex products. Hey, Tim, welcome to Altera.
Thank you. Thank you very much.
Thank you for joining us today. So can you tell us a little bit more about your company and your product?
Sure. My name is Tim Mao, and I'm the CEO of a startup company based in Toronto. And we started about 4 years ago. I think the BMI stands for Blue Waves Mobility Innovations. In short form, it's a BMI. It's kind of like easy to remember, right? And I say BMI is like body fat formula. Actually, I like to use this analogy. Is, we actually produce and dedicate our resource to produce the best open RAN radios, 5G and 6G for the wireless industry. And in order to do that, I think so the BMI means we are aiming to trim the body fat of the modern mobile networks for the operators. So I think that is what we do. Yeah, awesome. We produce the full range of the radios, 5G and 6G, outdoor high power and indoor low power, and with a purpose that then to take the right of this open RAN. So to be able to provide the best values, going forward, yes, for the industry. Yeah.
Thank you, Tim. Can you tell us, are there power or thermal constraints in your application?
Yes. So we design and develop, the radios, all in-house. And from our perspective is, the thermal considerations or design is almost everything for the radios. I think the reason behind it is very simple, because we are designing the things that wanted to pack the performance, the best performance, in a smaller and a smaller footprint. We wanted to make radios, compact as much as we can, and we wanted these radios to perform, which means can transmit as much power as possible. I think today, is what we can do. We produce almost the biggest, the power radios, transmit power radios in the industry. we do the dual band and ATRX, right? 8 channels. Each channels we transmit 80 watts. So altogether, I think it's 640 watts. I mean, this is kind of things desired by the operators. They want a bigger coverage. But however, in order to achieve that, consider that you have to balance the performance. You cannot shrink the radios forever because the heating problems comes out, right? And so despite the desire, I think we want to do a smaller radios, but we still have to think about and how to make sure that this radio can perform in a way that only a limited way to dissipate the heat, which is passive cooling, right? The fins. And many of our operators, they have active fans and to reduce the heat, but that becomes quite an obsolete design. So therefore, I think so we consider very carefully about the performance.
So tell us more. That's awesome. Tell us more about how the performance per watt advantage, the 2x that we've talked about in Agilex, how does that help in your application?
Right. And in our latest product, we partner with Altera and we picked up about Agilex, FPGA as a digital core. And I think one of the prime reasons to pick up this Agilex series is because of this superb power efficiency. This gives a lot of advantage. If you look at the thermal budget, if you look at the build product capital budget, right? The thermal budget is the most important budget, and we have to comply with. And this one affect all the aspects, all the factors of the radio. So from heat sink, as we just mentioned, and many others like height of the fins, whatever. So in order to make that compact, and we have to consider all these the factors. And so today, I think our radio just displayed in this building. You can see today our radio is almost comparable from the size-wise, right? From dimension-wise, comparable to the traditional radios produced by other tier 1 vendors. Almost similar. So those radios are silicon-based. Well, I think so. Our radio is Open RAN is based upon this Agilex FPGA. So I think this alone is an amazing achievement from my perspective. And secondly, okay, with that kind of more luxurious than brought by the efficiency of the digital core, we actually can optimize the components around the FPGA. And today, our latest, the radio is still on the stage from the beta to alpha. The BOM is not fixed yet, but we can see by optimizing these components around the FPGA, we're able to achieve savings quite significant from the digital core part compared to our old generations that based on the competitive solutions of FPGA, and we can say almost achieved a 10% cost savings in the component. I think that is alone is very significant from the radio perspective. Right now, is the market is getting so competitive. So that is why I think so. We believe we made the right choice.
Perfect. Thank you. Thank you so much for sharing that insight. And as Tim also said, right, the performance per watt advantage can play in different ways for different customers. I mean, you could use the performance advantages if you're very speed sensitive, or you could trade off some of the performance, use a slower speed grade perhaps for even better power, and overall your cost structure comes down. So that's sort of what Tim was saying. So thank you very much, Tim. Really appreciate you being with us today.
Thank you very much.
Yeah, and hope you have a good day.
Altera, accelerating innovators.